Welcome back to our Chem 152 video series. In this video, we'll talk about how to solve problems that involve first and second order decay. We'll begin with an example that uses first order kinetics. In this question, we are given the half-life and we are first asked to find the rate constant K. The equation for the rate constant, if you are using first order kinetics, is Ln of 2 divided by h, which stands for the half-life itself, will give you the K. So here we'll take Ln of 2 on top and 5,000 on the bottom. If we divide, we will get 1.39 times 10 to the negative fourth. Since the units on the bottom of this fraction are years, we will write inverse years as our answer for K. Next, we are asked to find the percent remaining after 12,000 years. For this, we'll use what's called the integrated rate law equation. The integrated rate law says we're going to take Ln of A final divided by A initial equals negative KT. We'll briefly go over what each letter stands for. A final will be our ending amount of whatever compound we're dealing with. A initial will be the starting amount of whatever compound we're dealing with. K will be our rate constant, and T will be the amount of time that's passed. We already know what K is. We'll check that off and we'll write the number next to the K over here on the right. That's 1.39 times 10 to the negative fourth power. We also know that 12,000 years have passed, so we also know T. We'll check that off as well. It seems like we may not have the starting amount or the ending amount, but anytime they ask you to find percent remaining, our starting percent will always be 100. This will be true anytime you're doing a percentage problem. Therefore, we'll say A initial is 100. We'll check that off. And then we'll say that A final, our ending amount, is not known. We'll box that in the equation. We're going to have to do some algebra to solve for A final, though. You may notice that the A final, which we're trying to solve for, is inside of a natural log. So we're going to use a base E exponential on both sides. If we take that base E exponential, we'll end up with A final divided by A initial is equal to lowercase e raised to the negative kt. Let's remind ourselves that we are still going for A final. Now we can multiply both sides of the equation by A initial. If we do so, our new equation will be A final equals A initial times lowercase e raised to the negative kt. Now that we have A final by itself, we'll place each number in the correct position. A initial was 100 because we had a percentage problem. Multiplied by lowercase e raised to negative k, which is 1.39 times 10 to the negative fourth, multiplied by t, which is 12,000 years. If we place all of this in a calculator, we will get 18.95% remaining. This will be our final amount of radioactive compound after 12,000 years have passed. Now we'll work a similar question. However, in this question, we'll be using second order kinetics instead, and that's going to change a great deal of the math. This time, finding the rate constant is going to use a different equation, and that equation will be 1 divided by the half-life multiplied by the initial concentration, A. Our half-life is still 5,000 years, and we'll say H is 5,000. Our initial concentration is 0.1 molarity. We'll say A initial is 0.1. Therefore, our lowercase k value is 1 over 5,000 times 0.1. If we do the math, we'll end up with 1 over 500, giving us 0.002. For the units, half-life was in years, and A initial was in molarity, therefore our units will be inverse years, inverse molarity. Part B asks us how long it would take for the concentration to drop to 0.01 molarity. It turns out we can use an integrated rate law for this as well, but it's going to look different from the first-order kinetics version. The integrated rate law for second order is 1 over A final minus 1 over A initial is equal to K times T. Now we know that A initial is 0.1 because that was used in the previous part of the problem. We know that the K value is 0.002 inverse years, inverse molarity. And now we are also given that A final is 0.01. Therefore, we'll check off A final, A initial, and K, and our unknown will be time. Now we'll plug our known numbers in and try to solve for the unknown. On the left side, we'll have 1 divided by A final, which is 1 divided by 0.01, minus 1 over A initial, which is 1 divided by 0.1, equals 0.002 for our K, multiplied by our unknown time. If we divide, we'll end up with 100 minus 10 equals 0.002t. 100 minus 10 is 90, still equals 0.002t, and therefore our time is 90 divided by 0.002. If we divide, we'll end up with 45,000 years. Therefore, it will take 45,000 years for our molarity to drop from 0.1 down to 0.01. And so this is how you can use the integrated rate laws for both first order and second order. Thank you for watching. We'll see you again soon.